Hi everyone, I'm Tyler Wolf, and today we're going to cover the fundamentals of agentic AI. Specifically, we're going to be focusing on an introduction to large language models, RAG, and agents. This is a concept plus demo session, so we'll spend about 15 minutes or so building the mental models and understanding the concepts, and then I'll show you how to build a working RAG agent in using Flowise, and there will be absolutely no code required. So that way, by the end of this session, you'll understand not just what these systems do, but you'll also be able to apply this and build them yourself. Okay, so before we dive in, let me set some context about where I'm assuming that everyone here is starting from. On the left here, you can see that I'm assuming, essentially what you already know, that you've used ChatGPT or Claude Code or more similar, large language model tools, that you're comfortable with APIs and some technical concepts, and that you have at least a few years of professional experience. On the right is what we would expect that you'll learn today, essentially how large language models actually work underneath the hood, why they hallucinate, why they have knowledge cutoffs, what RAG is and why it helps to address some of these challenges and why it matters, and then also how agents build on top and extend RAG with reasoning and tool use. If some of this is a review for you, that's perfectly fine. The demo will be where things can get hands-on, and hopefully you learn some more and how to apply it there. Okay, let's start with a mental model for how large language models work. At their core, LLMs are next token prediction engines trained at massive scale based on upwards of a third of the corpus of content on the internet. So you're able to give them a prompt like the capital of France is ... and then they will predict the most likely next token, which in this case would be Paris. That sounds simple, but there's a surprise. Essentially, at sufficient scale, hundreds of billions of parameters are trained onto these models. This pattern completion of essentially just predicting the next token or the next word or the next phrase very starts to look like advanced reasoning and can lead to code completion, which is where we have the advent of essentially coding agents being powered by large language models and foundation models, and also creative synthesis, such as some of the generative and diffusion models creating powering things like Sora or image creation or Nano Banana by Google Gemini. So on the right, I've listed three key concepts. First, you have training. LLMs are compressed representation of their training data. They are not essentially databases that contain and store all of the data. Instead, the models have learned the patterns across this data, across all of the language that they've been trained on. Second, you have capabilities. This simple mechanism gives us summarization, translation, code generation, analysis, creative writing, and also multi-turn conversations. And then on the third, and this is the analogy I want you to remember, think of an LLM as a brilliant colleague who reads everything but wasn't there yesterday. So they have vast knowledge, but it is frozen in time. So the models have essentially information up to the date to where their last training run was performed. So without tool use or other capabilities, they may not be able to do things like tell you what today's date is or tell you what the price of a stock was last week. So the frozen in time part is going to be important, and we'll see why as we continue on. Okay, so large language models are incredible. They're very powerful. Why can't we just use them directly for everything? And as we discuss, or at least started to discuss in the last slide, they do have several fundamental gaps. One of the first gaps being knowledge cutoff. Training data has a fixed date. And so the model, if it wasn't trained yesterday, it doesn't know what happened yesterday, last week, or after the training ended, which could be as much as 1 to 2 years prior, depending on the model that you're working with. And so if you ask it who won the Super Bowl, it may or may not know the answer if that was last year. If the Super Bowl was last week, most likely, if you're using one of the common models or interfaces like ChatGPT, it, without tool use, does not. It cannot answer reliably those things. Another is hallucination. This is one of the big ones with large language models specifically, and that's because large language models are probabilistic machines, right? They're generating plausible sounding text even when they're uncertain. And their confidence does not necessarily mean correctness. It essentially means that this was the most likely next text that it predicted, but that doesn't mean that it is factually true just because it is the most likely based on its estimations. So if you ask it for your account balance and it has no reference in order, or no tool use or access in order to get your account balance, it may just make up a value that sounds very plausible and may even sound confident in its response returning back to you as a user. The third one is actions. So LLMs essentially generate text. Other types of models, generative models, may generate images. They can't do things natively like send emails, query databases, book a flight for you, or really interact with any external systems. They can describe the steps, they can articulate them, they can generate plans, text-based plans, but they can't actually do those things. So here's the kind of key insight at the bottom. That ultimately RAG is what we use to solve for gaps 1 and 2 around knowledge cutoff and hallucinations. And then agents step in to solve gap 3 because agents are essentially how we will reason and then perform actions, actually do things out in the world. And so together we can kind of combine all of these capabilities into a real production AI system. And we will start with looking at RAG first. Okay. So to address some of the challenges that we just discussed, specifically around knowledge cutoff and hallucinations, enter RAG. RAG stands for Retrieval Augmented Generation, and let's essentially walk through how that works. Following the flow from the left to the right, essentially a user asks a question like, what is our refund policy? And instead of sending that message directly to a large language model, we will first send it to a retriever. This will search through a vector database using semantic similarity, essentially not just looking for keyword matches, but looking for contextual similarity. And then the retriever is going to go and find documents that are most relevant, or document chunks within a document that are most relevant. These could be things from policy PDFs, wikis, websites, employee or other company manuals, and it's going to go through potentially and find relevant FAQs for this search, like around refunds and around policies. And so now we are going to send our original question and the context that the retriever essentially retrieved and synthesized, and we're going to vend both of those things to the large language model. The large language model then is going to have more context, and it's going to generate an answer that is grounded in actual documents, and the output is a response that's cited, it's accurate, and it's based on our specific data. It's not just based on what the model's more general training data is. So down below I've highlighted 3 things. The knowledge base can come from your documents, your PDFs, your databases. This is all converted to vectors, which we could talk about a little bit further for semantic search. And then the magic here is that the large language model sees the relevant context from your policy before it generates a response. So it answers based on your data, not just based on its training. This improves the result accuracy. It also ensures that it has up-to-date information that may not be in its training data, and it reduces the risk of hallucinations, which can give you more verifiable answers. So this is a pattern that's used by places like Microsoft Copilot, Perplexity, and many enterprise search systems built on top of large language models at this point. So on the previous slide, we just talked through a little bit about how RAG works, and this is an analogy that should make it a little bit more easy, or easier to kind of understand or grok. On the left, you have essentially a large language model by itself, and this you could view as taking a closed book exam. You have to recall everything from memory. Your knowledge is frozen at study time. You're confident even when perhaps you're uncertain, and you can't verify your own answers. Versus large language models plus RAG is more like having an open book exam. You can reference the textbook, you can cite the textbook, you have access to the most current materials, all available materials, even if they've been updated, and so you can ground your answers in exact documents, pages, subsections, or chunks, as they're more frequently called in RAG. And you can cite where you found the information in order to kind of prove verifiability. So the key insight at the bottom, and this is important, that RAG doesn't make the large language model any smarter. It doesn't augment the weights or training of the model itself. However, it does give the large language model the right information at the right time to reduce hallucinations, solve for the knowledge gap, and improve verifiability of responses. So the model's reasoning capabilities stay the same. We're just improving what it has to reason over and give a more accurate response. Okay, so time for a quiz check. What problem does RAG solve? A, makes LLMs run faster and use less compute. B, grounds LLM responses in specific retrievable knowledge. C, allows LLMs to learn new information during inference. Or D, replaces the need for fine-tuning on domain-specific data. Take a few minutes based on what we just discussed, looking over the prior slides, and make your best guess. Pausing for dramatic effect. Hopefully you guessed correctly with option B. RAG is grounding the LLM's responses in specific retrievable knowledge. Remember, the component that we discussed is called a retriever that essentially goes and does semantic search to find the most relevant documents, document chunks, PDFs, policies, in order to then that back to the LLM so that it gives higher fidelity, more accurate answers. So the correct answer in the quick check is option B. Okay, so we previously learned that you can extend LLM's capabilities by leveraging things like RAG. We will continue down that value proposition by going even beyond RAG to focusing on agents. You can think of agents based on their 3 levels of capability. One, you have the base LLM, which can generate text. It can describe how to book a flight, for example. Then level 2, you have the large language model plus RAG, which can generate text and also retrieve relevant information. It tells you your specific refund policy takes 5 days because it looked it up. And then next, you have level 3, which includes the agent, which can reason, retrieve, and now act. It can actually process your refund and tell you to check your email based on the confirmation that it just sent you. So what makes an agent an agent? First, we have a reasoning loop. This is the ability to break down complex tasks, plan through steps, and iterate them based on results. Essentially think, develop a plan based on that thinking, execute through that plan, and then based on the outputs, essentially respond and continue to iterate and refine and keep moving forward until you've accomplished the goal. Next, you have tool use. Agents can call external APIs. They can query databases that they have access to. They can execute code through a codex. They can even use your browser and browse the web and use websites and tools just like humans do. And they can interact with backend systems that they've been given permission to do. You also have memory. This is key because they can maintain their context essentially across steps, and they can learn from intermediate results. If they were executing a plan, for instance, and found that they ran into a permissions issue or that it didn't execute as expected, they can go back and investigate through the logs, what happened, what failed, and then develop additional steps to address that and remedy that issue before proceeding with their original plan. You've most likely seen examples with this. Claude Code. We now have Claude Cowork for computer use. You have GPT Actions, and then you have coding agents, things like Devin and others, and very many of them follow this pattern, whether you're aware of it or not. Folks may be building apps in a few minutes using things like Replit or Lovable or Gemini, and very many of them are using LLMs plus RAG plus agents, following this reasoning, tool use, and memory loop. So in the previous slide, we talked a little bit about how agents work and essentially this reasoning loop that they follow through. This is formally called widely across the industry as the React pattern. You'll frequently in agent papers, white papers, and things of that such, you'll hear and see the term React. And this essentially is just the combination of reasoning plus action or acting. And most agentic systems are built on something called React at this point. It's really just a loop with three primary steps that the agent is looping through until the task or project or plan is done. Step one is the thought process or thinking, and this is where the agent is thinking about what it needs to do. So when a user asked it or prompted it for a question, or a system asked it to do something or answer some question, and so it's thinking through this. For example, like I need to find a user's order status. I should query the orders database with their email address. Step two is action. The agent executes a tool call. In this case, it could be a queryable interface to where it's able to query orders with the user's email. And then step three is observation. The agent is going to see the result. It's going to see order 4521, status shipped with an ETA for delivery of January 24th. And then this loop is going to continue. The agent's going to think again and say, okay, I have the order info. Now should I format a helpful response for the user? And then the thought, action, observation loop is going to repeat until we are satisfied with the output. And this is really the foundation for how agents break down complex tasks into manageable steps. And then each cycle gets us closer and closer to that end state goal. There is a paper where this was introduced from 2022. It's worth a Google search, just React white paper 2022, and it is worth a read if you would like to go deeper on the concept. Okay, so we've been talking a little bit about agents, React, and essentially how they work. Let's look at some of the more specific building blocks for agentic systems. So at the top here, you'll see we have a user request is coming in, and they're saying, hey, help me analyze Q4 sales. This request is going to first go to the brain, which you can kind of think of as your LLM core plus system prompts, and this is going to produce a response. And next, the brain is going to vend this to the executor, and we're going to have an executor, which is going to handle the actions and the runtime. We're going to have knowledge or knowledge base, which benefits from, we were discussing RAG. You're going to have tools and external capabilities, and then you're also going to have memory for context, as well as to store files and outputs along the way. Just working from left to right, we have memory. You can think of what's going into memory: conversation history, if this is going to be a multi-turn conversation with a user or another system. You're also going to have previous tool results. We may have handled a request like this over and over again, and so we may have an index of previous tool results, and also likely a long-term vector store. That can help us improve performance of these systems over time by having storage of many of our conversations, not only with this user, but also potentially other users who have very similar requests, which can help the system more reliably get to the right output or the right reasoning chain, or essentially pre-identify the right actions leveraging this memory. The crux we were discussing of agents is on the action side, so tools. These are going to be external capabilities. They could be web search, they could be calculators, they could be database queries and data connectors, APIs to other services. Like if you wanted to book a flight, potentially the agent could use a web interface like we would to log into a system and book a flight, but there is also very likely an API through one of the booking services that has an API that you can get developer access key for, and that would allow our agent to use the API to book a flight instead of using a web interface. And then also code execution. They may need to write some Python code in order to understand some of this data, in order to analyze it, or as a part of some other execution process. Next, we have knowledge. So this is very likely to be a vector database, which is efficient for storage. And this is going to have documents, PDFs, text files, they could have emails, anywhere where we're going to have relevant information that can help throughout this reasoning and action chain. It's going to be stored in a knowledge base, likely in a vector database. And then you have the executor. This is really our runtime for the application. It's running the tool calls themselves. It's handling any error outputs along the way, and then it is ultimately returning our output, to our user. So this is, these aren't necessarily the exact implemented components, but when you're designing agentic systems, you can kind of think about these as the kind of mental model for building blocks. And if you go to use a framework like LangChain or Llama Index or Flowise, you will see that even though some of the names of the tools and components will be differently, likely lots of the actual components will map to one of these building blocks, which we will be getting into as we do our Flowise demo itself. Okay, so we spent a few minutes now learning about concepts from LLMs to RAG to now agents. Let's stop with the concepts and start on the application side. I'm going to show you how to create a RAG-powered document Q&A agent using Flowise. We can go, once we're logged into Flowise, we can go from a completely empty canvas to an actual working system that actually can deliver on meaningful business value, answer questions like we would commonly have in customer support and Q&A in just 5 to 10 minutes of work. The knowledge base here we're going to use is a customer support document, and this would be for a fictional e-commerce company. And let's get into Flowise and see it in action. Okay, so now that we've learned some of the concepts of an agentic system, including the large language model itself, RAG, and then the REACT, reasoning plus action loop that agents follow, we're going to apply this and going to build something that actually works in just a few minutes using Flowise. I've pre-recorded my steps using the Flowise's Canvas editor, but you feel free to set up a free account to log in and do this for yourself, and then you can certainly build, remix, expand on from there. So getting to it, if you go to Flowise, you should be able to get started. Like most websites, they accept Google login via Google, so they don't necessarily have to set up an account if you don't want to. So we'll go ahead and log in, or in this case, sign in with Google and get started. Once we log in, it will take us to essentially this list of chat flows. Here, this is what we are going to be building. We're going to be building a chat flow. If you want to, you're welcome to explore all the other additional, more complex things that Flowise has to offer, but the easiest way to get started is by creating a new chat flow. So that's what we're going to do here. You'll just navigate over to that big plus button here on the right hand side and click Add New. Once you click Add New, it's going to take you to the canvas. The Flowise canvas is really, you can think of this as Figma, but for AI. So it kind of looks like a design whiteboard where you can drag and drop components. But in this case, you're not just designing what they might look like, you're actually doing drag and drop to design a real working agentic system. So the main canvas here is where we build. Each node that we're going to drag onto the screen represents a real component, and then the connections that will form between the components is the data flow through them. So that's essentially how Flowise works here on the canvas itself. To get started, we're going to go ahead and start with adding a PDF loader. So you'll see this PDF file on the side if you click the add button and then you just search PDF. We need to first ingest our knowledge base. So I am adding a PDF file loader. I'm going to upload, we have a PDF file called TechFlow, which is our fictional company, support knowledge base. And it's basically a 10-page document covering orders, shipping, returns, billing, and troubleshooting. And this is exactly the kind of document that we would expect customer support teams to reference throughout the day as they handle incoming requests. So we're going to create the component to support this. It's as simple as dragging it onto the screen. And it builds this pre-built component, zooming out just so that as we add more things onto the screen, you'll be able to see them. And then there you can see we're just attaching the PDF file that we want the PDF loader to use. The loader is going to automatically chunk the document. I've set the chunk size to 1,000 characters with an overlap of 200. This means that each piece is going to be substantial enough to contain complete answers. That's the goal. And then there is going to be some overlap. And we're telling here, you can say one document per page if there are different documents, but in our case, we're going to switch that usage over to one document per file, and that just lets the system know that this entire PDF is just one document. It's not a collation of many documents. And so a question about refunds will retrieve the full policy from this document that it can find about refunds. It won't find necessarily just a cutoff snippet by having too small of a chunk size or searching too little of the document. So that's what we see there on screen. Like I said, just switching to one document per file there. And yeah, getting started with using our PDF knowledge base is as simple as that. Next, we're going to go and continue on with our next component, and we're going to add embeddings. So we're going to use OpenAI embeddings. Essentially what this is going to do is it's going to convert our text chunks into vectors. We talked about that. Vectors are more storage efficient. They're numerical representations that capture the semantic meaning across our text. And so we're going to set that up. And important note here is to use OpenAI embeddings, it does require that you have an OpenAI developer key. So you can, you may already be a user of ChatGPT. If you go and create an API key, you can essentially create new, as you see on screen here, and link your API key from your personal or developer account with OpenAI to Flowise, and that will allow you to essentially do API calls to OpenAI services from this Flowise, which is required to make it work. You could use some other, they support many other solution providers and language model providers besides OpenAI, but since I already had an API key, I'm using that, and it's also one of the common ones for this demo. So I've already created an API key and stored it here, so I'm just selecting it, but you would go to create new if you were doing this for the first time. And so this is where, essentially we're going to be able to, we have our PDF file, we now are setting up OpenAI embeddings, and this is what's going to essentially allow for the magic to happen to where when our users or our support POCs have a particular question that they need answered, it's going to be able to run a retriever and search through our documents using the vectorized embeddings through OpenAI. So that's the purpose there. We are using a fast and cost-effective it's text embeddings ADA 002. You probably don't need to know that much detail, but just so you know, it is very fast and cost-effective. It's not going to cost probably less than a couple cents to run through this loop repeatedly on our side. So next, now that we have embeddings and a PDF file, we need to set up our vector store. We need somewhere to actually store the information that we're going to generate. So we'll do that as our next step here. So we're going to use an in-memory vector store. And this is essentially somewhere where we're going to be able to embed and store our documents, and it's going to enable a similarity search for our agent. So just like the other components, you're just going to drag and drop it on screen. And then you'll see that it has these two inputs. So we haven't done any node connections yet, but you'll notice on screen that the PDF file has an outflow here, and the OpenAI embeddings has an outflow here. And this in-memory vector store has an inflow, two inflow connectors on the left side. And so we are going to make these connections from document to document, and then from OpenAI embeddings to the in-memory vector store embeddings. It's as simple as that. We now have actual, production-ready connections between these components with basically just that click and connect. So in production, you would likely want to swap from in-memory to something like Pinecone or Chroma Those can handle millions of documents, and they would also persist across sessions. Since we're using in-memory, this will only persist and only be essentially stored and useful while you're using this in the app session itself. So it works perfectly fine for this instructional demo, but yeah, Pinecone and Chroma are kind of two of the more common vector stores that you'll see developers using out in industry today. So next, we're going to add the chat model itself. So this is a chat bot, so we're going to use Chat OpenAI. Since we're already using OpenAI for the embeddings, we are also going to use OpenAI for the chat component here, and we're going to use the same key that we had already created. So you don't need to create a new key in this case. You can just use the key that you created for the first step with the embeddings. We are going to use this model, which is small, fast, and efficient. You could use many other, you'll see there are dozens of other model options there. And we're also going to change the temperature. So the default temperature is 0.9. That means that there could be lots of variability in the responses. There are pros and cons for that, but in our case, we're handling customer support requests, so we want more repeatability and reproducibility, and so we're going to reduce the temperature down to 0.3, which is what that means. And this is because we want consistent factual answers for customer support. We don't want as much creativity like you would potentially benefit from in other use cases. Moving on, we are going to create a chain. So in this case, this is essentially the component that you can think of that ties everything together. You can see it has 4 inputs flowing in. So we have the chat, OpenAI chat interface. We're connecting essentially the chat model that we're choosing to use, and then we have a vector store retriever, and we have memory. And in this case, we do want to return source documents, so we're toggling that on. And what that means is that when our chatbot answers a question, we want it to cite essentially where it found that information in a way that you could click that and follow through and see that information yourself. That increases trust and increases verifiability and just ensures that we're making factual claims. The model isn't hallucinating and making up information. Okay, so I've enabled return source documents, and we can see the chunks. And so now it's as simple as saving. So before you can run all this, you do need to save. And that's just because there is some different state, like the API keys that you selected, those kinds of things that won't, until you save, those things won't essentially be stored and usable. So we do want to go ahead and essentially save. Instead of an unknown chat flow canvas here, we'll now have a saved named canvas that you can essentially come back to, build upon. You can also duplicate it and make another version. And so now everything's saved, and we have a running workable canvas. Everything appears to be in good shape, and all of the components that we built ultimately all flow into this final output component, which is the conversational retrieval QA chain. So the final step is to start doing some testing. Flowwise makes this very easy. You'll see that green chat icon up in the top right. You essentially click that, and it will open up our chatbot. And we're going to ask it a question. What is your return policy? And see what it says. Take just a couple seconds, and there you go. Just after a couple seconds, it answers. We'll see that it provides a reasonable output, explaining that there's a 30-day return policy, products must be unused, original packaging, things that you would expect potentially to come back from an e-commerce company, as well as the fact that gift cards specifically are non-refundable. And then importantly, since we selected to toggle on return source documents, you'll see this at the bottom, which you could hover over and click when you're using this to build yourself with any PDF that you select, and you would actually be able to click this TechFlow and document, and it will open up the relevant chunk that was used for this retrieval. So it works on this question. Seems like a good start. Let's think about what other questions we could try. So we'll kind of adjust so that we can see the whole thing and our chatbot, and we'll try a few more questions. Trying to think here, what are some good additional questions for us to ask our chatbot? Yeah, here's a good one. How long does it take to get a refund? That's always important question for customers. When will they get their money? And there we go. It's also able to successfully answer that once we receive and inspect the return, it's going to take about 5 to 7 business days in order to get a refund. Let's see what else. Yeah, I received the wrong item. So let's see what I can do about that. Okay, and yeah, in this case, the chatbot is showing empathy. It's apologizing for the error, and it's requesting that we contact customer support about this issue so that we can understand why the item was wrong, what happened, and get a refund, as well as try to get us a new item. And we're essentially just following up to say, hey, what if the correct item is actually out of stock? In which case, they provide feedback that they will give us a full refund if the correct item is no longer in stock. And so it's as simple as that. We actually went from concept to something that works. This could be deployed. Obviously, this is only a 10-page PDF, but if this were a 100-page document with all of the comprehensive customer support policies or common service handlings, this could actually be a very useful chatbot. It's already helped us answer our questions we have about getting our refund at this fictional e-commerce company, and it's also shown us how we can easily implement an actual working agent architecture using Flowise. Okay, so we're now back to our slides, and in just about 8 minutes or so, we built a customer support agent that is able to ingest a PDF knowledge base. It embeds and stores it for semantic search. It retrieves the relevant context for each question that the customer asks, and it generates an accurate and grounded response. And it even cites its sources so answers can be verified and maintained. And we built this, with no coding ability, no infrastructure that we had to set up. And this is the same patterns that power AI support agents at many companies, beyond our fictional e-commerce company, to many, large, public enterprises. So now let's kind of bring home both the concept and the demo with 4 key takeaways. One is that LLMs are powerful, very powerful pattern completers. They're not knowledge bases though. They excel at reasoning and generation, but they have knowledge cutoffs, they can hallucinate, and understanding this limitation is very important as we develop solutions on top of them. RAG comes in to ground our responses in your specific data. It can retrieve content and relevant context before generating, and it helps us get accurate, verifiable, up-to-date answers. It's the open book exam approach that we discussed in our analogy before. And the next, here comes agents. Agents add reasoning loops and tool use, and we generally follow the React pattern where we think, we act, we observe, and then we repeat as needed. And we kind of follow this multi-step problem solving loop until the job is done. And then fourth is you can build production-ready agents without code. Beyond Flowise, there are many others, Make, N8, and dozens of platforms, Google search or even use ChatGPT to recommend some for you. And you'll find very similar platforms like Flowise that we used to produce our demo here. At the bottom, I've listed kind of where you can go next if you want to go deeper. There's multi-agent systems that you can explore. You can get into things like Crew AI and AutoGen. You can use much more advanced RAG strategies than the simple PDF embedding and vector DB that we use, like re-ranking or hybrid search. And then there are whole agent evaluation frameworks to ensure that many different types of agents are essentially working as expected, that they're continuously improving, and that they're delivering the right customer experience for our production users. And then also production deployment patterns. Obviously here, we learned the concepts, we did a demo, we got something that actually works, but to do this at scale to handle millions of customer requests every day, There, are production deployment considerations and patterns that we would want to learn to do that. But overall, I hope this was useful across the slide content as well as the Flowise demo. Hopefully you'll take the time and kind of build this yourself in Flowise, save it, and then kind of go from there and see what interesting agents you can build on your own. Thanks.